So far, we've learned that a system contains some total amount of energy which can change if energy is transferred into or out of the system. There are three mechanisms by which energy can be transferred into or out of the system: heat transfer, work transfer, and mass flow. Recall that our goal is to create a mathematical expression for the first law of thermodynamics, or conservation of energy. We can write an equation which represents the change in the total energy of the system during a process by accounting for all of the energy transferred into and out of the system during that process. The total change in energy of the system during a process, delta E, is equal to the total amount of energy transferred into the system by heat minus the total amount of energy transferred out of the system by heat, plus all of the energy transferred into the system by work minus all of the energy transferred out of the system by work, plus all of the energy contained in the mass that enters the system, minus all of the energy contained in the mass that leaves the system. This equation is called an energy balance. Let's take a closer look at the energy transferred into the system by mass flow. Suppose there is some fixed amount of mass that will enter our system during a process. Let's determine the total amount of energy contained in this mass. We'll take the mass as a separate system. Recall that the total energy contained in a system consists of the internal energy, the kinetic energy, and the potential energy of the system. There is also some work required to push this mass into our system. This is called flow work, or flow energy. We can think of the flow energy as the energy required by an imaginary piston to push the mass into our system. Suppose the mass that will enter our system is at some pressure P, and that it has some volume V. The force applied on the mass is equal to the pressure of the mass times its cross-sectional area A. In order to push all of the mass into our system, this force must act over the entire length of the mass, L. The flow energy, then, is the force times the length. This can be expressed as the pressure times the volume. This flow energy is added to the total energy of the mass that will enter our system. We can rearrange this expression as follows. The internal energy of this mass and the flow energy required to push it into the system can be combined to form a new property denoted by the letter H. This property is called enthalpy. We can write the total energy contained in the mass that has entered our system in terms of enthalpy as follows. A similar analysis can be performed on the mass flowing out of the system. We can now update our original energy balance with these new expressions for the energy flowing into and out of our system with mass. We will rewrite the energy balance in a more general form as follows. The change in total energy of a system during a process, which equals the change in the sum of the internal energy, kinetic energy, and potential energy of the system, is equal to the sum of all heat transfer interactions with the system, plus the sum of all work interactions with the system, plus the sum of all of the energy contained in the mass flowing into the system, minus the sum of all of the energy contained in the mass flowing out of the system. Let's make one more change to our equation. Right now, the total enthalpy of the mass entering and leaving the system are denoted by a capital H. This is an extensive property, which means that its value depends on the size or extent of the system. If we divide this by the total mass, we end up with a specific property. A specific property is an extensive property per unit mass. Specific properties are usually denoted by lowercase letters. Here, the specific enthalpy is denoted by a lowercase h. We can write our energy balance in the following form, where the total mass in and out is multiplied by the specific enthalpy, the specific kinetic energy, and the specific potential energy of the mass flowing in and out of our system. This equation represents the energy balance of our system for some process. It is a mathematical expression of the first law of thermodynamics, or conservation of energy.